Yeah, hello, good evening. Welcome to another wonderful session on Not on Evaluation Physics. My name is Mr. Duro, the regular host on this program. In today's class, we're basically looking at alternative to practical physics, WAEC and NECO GC in perspective. I know quite a number of you are not familiar with the way questions are set in practical physics alternative, especially when you're writing for WAEC and NECO GC. So I'm literally going to put you through what the nitty-gritties of answering questions in alternative to practical physics and getting maximum mark from the exam. So sit back while I explain all of the details to you. So basically, alternative to practical simply means the practical is not going to be experimented. You're not carrying out the experiments like you used to do in the classroom or with your teachers in the laboratory. Somebody has already done the practicals for you, and it is the observations from those practicals are expressed in diagrams. So the only responsibility you really have is to deduce those observations from those diagrams. And now I'm going to be teaching you the various kind of diagrams you can see in the laboratory practicals and how you can deduce those observations from the diagrams. Now, but before I go into that, let me tell you there are three practicals that will be given to you during the exam. It is your responsibility to choose the easiest two out of the three. You're expected to answer just two questions out of the three. So this is your time, it is your responsibility to find those two questions that are relatively easier compared to the last one. And every time you're doing this practical physics, there's always one question which is quite tougher compared to the rest. So you need to take your time before you select those two questions you'll be answering. And so some students make this mistake. They will have attempted a question, and in the long run they will discover that the question is tougher than it seems, and then they will cancel their practical and move to the next one. That is not allowed. Let me repeat that word. It is not allowed in alternative to practical questions. So that is why it is good you set aside about 1 to 2 minutes to select which one of those questions is relatively easier, and then you make an attempt on it. So like I was telling you, alternative to practical questions are actually one of the easiest ways to get as many marks as possible in your physics exam. As a matter of fact, the questions carry up to 50 marks, which will be converted into 45 as the case may be, or 50 as it were. So you stand a good chance of getting a distinction in your practical physics, and in fact in your exam physics as a whole, if you pay attention to details on this alternative to practicals. So like I said, there are three practicals. You choose the best two which is most convenient for you. And you don't start the practical unless you're sure you're going to finish it. Now, having selected your best two, okay, make sure that your observation table, follows the rules of writing observations. Your quantities in bracket the units of each of those quantities on top of the table. No single value in your table must stand as a whole number. As a matter of fact, the least decimal place you can have in every table is .0. Even if it's a whole number, you write it as put a decimal point 0 at the end of the figure. It's very important so you don't lose marks. Okay, so from the observation table, you go to your graph, then you determine the slope as well as the precautions, which I'm going to put you through on how you do that, so that you can get as many marks as possible. So let's look at the first one, which is deducing observations from diagrams. Like I said, your observation table carries the most mark in every practical physics exam, so you can't afford to joke with it. So let's look at these two tables, these two diagrams, and deduce values from them. Look at this one. I guess this experiment was carried out using the micrometer screw gauge as well as maybe the length of a wire or something. But figure 3A and figure 3B, I can see the section of a micrometer screw gauge, while figure 3C and 3D they represent the same thing, which could be the length of the wire or something. So looking at that micrometer screw gauge, for instance, For figure 3a, you will see that the last calibration there is just before 10. So my value there is what? 0.09 millimeters. If you go to 3b, the 3b also, the last calibration, okay, that I can see that coincided with the main scale is 4. So my value there is 0.04 millimeters. And if it is exactly on 5, then it will be 0.05 millimeters. Why the other one is what? 0.10 millimeters. Of course, I know you're familiar with the way the scales of micrometer screw gauge is read. So this screw gauge is actually not drawn to scale. Okay, it's not drawn to scale, so I can write the values the way it appears. But I must make sure that I put a decimal point in front. For instance, the 3A micrometer screw gauge reading, first one, I write it as 10, which is 0.10. Okay, on top of the table I have millimeters to deduce the calibration of the micrometer units, as well as that of 3B. So let's go to 3C now. Over 3C is the length of meter rule from 0 to 100 centimeters, and I have 5 B1, B2, B3, B4, B5, B6 all on it. But the important thing about this very diagram is that it has a scale. So pay attention to questions that do come with scale. This scale of 1 centimeter represents what? 5 centimeters. So in the real sense of it, whatever you measured using a meter rule, you must, or a small ruler, you must multiply it by 5. So my first reading here, let's say for instance from 0 to B1, okay, is 4 centimeters. Then I'll multiply it by 5 to give me what? 20 centimeters. And when I'm putting it on the observation table, I'll write it as 20.0. with maybe the length of the wire or something, whatever it is representing with this 0 to A to C, I'll put it on top of the table and put in brackets centimeters because I am measuring in centimeters. The same goes for figure 3D, which is very similar to figure 3C, but the difference is that the calibrations on this one looks a bit lower than this, so they are not the same thing. They do not represent the same parameters, but they are all measured in centimeters. And then the scale of this is the same thing as the scale of this. So whatever I measure with it, let's take for instance from 0 to B1, let's say it is 3.5, so I must multiply by 5, and that is about 16.5. Okay, now you need to be very careful also when you are measuring these values, because questions can come in a very deceptive way. They can put your 0 value on top of this line and put the 100 center at the bottom. This is your responsibility to deduce when to measure from this place and when to measure from this place. So you take precaution. And like I always tell my students, the observation table is very important. Whatever is going to cost to make sure you get it right. Because if you get it wrong, it's going to affect your graph, it will affect your slope, and also affect your precision. And I don't want you to lose any mark. So it's better you pay attention to details about the diagram that's given. This is just a case. Let's look at another one. This one is on electricity. Okay, so I'm going to start with this is a resistor box, and you can see from the note that is written here, they said what? Shaded circles are not active, while unshaded ones are what? Are in use. So it's my responsibility to find which one is unshaded and what it represents. For those of you that are familiar with using the resistance box, of course, you're going to put on top of your table, it will be R in brackets ohms, which is measured in ohms. Resistance is measured in ohms. Now looking at the first one, your first value there, R1, there's no unshaded box, so my first resistance is 0. Go to step 1. The only unshaded, circle is 1. So my R2 is 1.0 ohms. R3 is what? From here it is 2.0 what? Ohms. And then R4 is a combination of 1 and 2. So 1 plus 2 makes it what? 3. So R4 is 3 ohms. And then R5 is a combination of what? 2 and what? And 2, and that makes it what? 4 ohms. And then my R6 is what? 5.0 ohms. Like I said, no whole number must appear on your observation table. You must put at least a decimal point, even if it is 0.0. Very, very important, so you don't lose any mark. Now let's go to the ammeter. which is, of course, you can see that current is measured, or which I wish I could have shown you the way the questions answer, because it's very important you read through the procedure of the question. So to guide you through on what kind of instrument are you actually using, and the kind of instruments you're using really determine the precautions to state when you're stating your precautions for the experiment, because they will ask you to state at least 2 precautions taken, why if you were to perform this experiment. It comes with a strategy, and I'm going to put you through that in my next episode of this presentation. So looking at this now, I can see that the ammeter is calibrated from 0 to 1 to 2 to 3, right? There's nothing between 2 and 3, there's nothing between 2 and 1, so I have all these smaller calibrations between 1 and 0. And we count it very well. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is about 10 calibrations between 0 and 1. Meaning that what? That 10 dots are sharing just what? 1 ampere. So 1 dot is equals to what? 1 over 10, which is 0.1 what? Ampere. So my I1, okay, from here, if I'm not careful, I might think this is my I1, which is I6. No, I come to this place, which is my what? My I1, right? So my I1 is 3 ampere, 3.0 ampere. My I2 is 1.0 ampere. My I3 now is, I'm going to start from 0. Like I said, every of these dots represents 0.1. So this is 1, 2, 3, 4, 5, 6. That's 6 dots. And that is what? 0.6 ampere. My I4 is a very interesting position. As you can see, the pointer on I4 is neither on the 4th dot or the 5th dot. It is in between. Don't tell me your sight is excellent, so you can deduce that this is between 4 and 2, so that would be 4.5. No, that is very, very wrong. Anytime you're doing alternative practical question, what is important for you to deduce from a diagram like this is to look at the pointer and which of the dots is it closer to. That will be your value for that. So it's not responsible to be assuming that that is 0.5, no, or 0.2 or 0.3, no. So of course I'm going to go for what? The pointer is closer to 0.4, so I'll just go for what? 4. So my value is what? 0.4 ampere. Now going to the 5th current, which is I5. You can see I5 also lies between what? Between 3 and 4. And if you look at it closely, it looks as if it is closer to the 3 point than the 4 point. And of course, you've chosen 0.4 for the previous one, so the next one cannot be 0.4. So just go for what? 0.3 ampere, which one is great. And then the last one is what? Is closer to the second button than the 3rd button. So I'll just go for 0.2 ampere, which is great. So you've done a very good job by so doing. So there's a question that do come with dots. So it's a responsibility to know which of the dots the pointer is closer to. So you take your values. And then this one, very interesting, so to speak. It has about how many diagrams? 3 diagrams. We are measuring masses, we're measuring a depth of test tube in the beaker, and we're also taking time. Very interesting. Let's start from the masses. I'm going to take just 1 or 2 examples of this, and then you deduce the rest yourself. Now, I have the values on the scale for the masses is 0, 20, 40, 60, and 80. So in between 0 and 20 is 10. In between 10 and 0 is 5 dots. That means each of those 5 dots are sharing 10 grams. So 10 divided by 5, that is 2. That means each dot represents 2 grams, right? So if you look at the M1 carefully, you will see that the pointer is on the line between 40 and 60, and that's 50. So my first value is 50.0 grams. Make sure, like I said, you must put a decimal point, even if it's a whole number. Then go to M2 now. M2 is what? You can see the pointer is neither on the second point, the second dot after 50, or the first point after 50. So, but it's closer to the second dot, so I'll go for the second dot. And that is what? And that is 54. That is 2 dots is 2 times 2, which is 4. 4 plus 5, that is 54 dots. Great. And then for the stopwatch as well, you can see from 0 to 2 to 4 to 6. Between 0 and 2, we have a big line that represents 1. And in between 1 and 0, you have 5 dots. 1 divided by 5, that is 0.2. That each of the dots is also what? 0.2. So my first time on this is what? This is 6 right? This is 1, 2, and then I'm going to pick the third one because the pointer is close to it. And that's 3.